Hi, welcome to the ComSci 137 lecture. Sunny here. For this module, we will have a brief overview of routing. Let's start. The goal of the network layer is to deliver a datagram from its source to destination or destinations. There are some terms under this. Forwarding is the way a packet is delivered to the next station. Routing is a process of selecting a path for traffic in a network or across multiple networks. There are two categories. Unicast routing, if a datagram is destined for only one destination, and multicast routing if a datagram is destined for several destinations. In unicast routing, a packet is routed hop by hop from its source to its destination by the help of forwarding tables. The source host needs no forwarding table because it delivers its packet to the default router in its local network. The destination host needs no forwarding table either because it receives the packet from its default router in its local network. This means that only the routers that glue together the networks in the internet need forwarding tables. With the above explanation, routing a packet from its source to its destination means routing the packet from a source router to a destination router. To find the best route, an internet can be modeled as a graph. A graph in computer science is a set of nodes and edges that connect the nodes. To model an internet as a graph, we can think of each router as a node and each network between a pair of routers as an edge. An internet is modeled as a weighted graph, in which each edge is associated with a cost. In routing, the cost of an edge has a different interpretation in different routing protocols. For the moment, we assume that there is a cost associated with each edge. If there is no edge between the nodes, the cost is infinity. When an internet is modeled as a weighted graph, one of the ways to interpret the best route from the source router to the destination router is to find the least cost between the two. In other words, the source router chooses a route to the destination router in such a way that the total cost for the route is the least cost among all possible routes. A least cost tree is a tree with the source router as the root that spans the whole graph and in which the path between the root and any other node is the shortest. In this way, we can only have one shortest path tree for each node. Routing protocols can be categorized in many ways. One can be based on their domain of operation. There are two subcategories under this: intradomain, which is used inside autonomous systems, and interdomain, which is used between autonomous systems. Under the intradomain are the distance vector and link state routing protocols. RIP is a sample of protocol under distance vector, while OSPF is a sample protocol under the link state routing. Under interdomain is the path vector protocol, in which BGP is an example. In distance vector routing, the first thing each node creates is its own least cost tree with the rudimentary information it has about its immediate neighbors. The incomplete trees are exchanged between intermediate neighbors to make the trees more and more complete and to represent the whole internet. We can say that in distance vector routing, a router continuously tells all of its neighbors what it knows about the whole internet. The heart of distance vector routing is the famous Bellman-Ford equation. This equation is used to find the least cost between the source node and the destination node through some intermediary nodes when the costs between the source and the intermediary nodes and the least cost between the intermediary nodes and the destination are given. The concept of a distance vector is the rationale for the name distance vector routing. A least cost tree is a combination of least cost paths from the root of the tree to all destinations. These paths are graphically glued together to form the tree. Distance vector routing unglues these paths and create a distance vector, a one-dimensional array to represent the tree. Note that the name of the distance vector defines the root, the indexes define the destinations, and the value of each cell defines the least cost from the root to the destination. A distance vector does not give the path to the destinations as the least cost tree does. It gives only the least cost to the destinations. A routing algorithm that directly follows our discussion for creating least cost trees and forwarding tables is the link state routing. This method uses the term link state to define the characteristics of a link that represents a network in the internet. In this algorithm, the cost associated with an edge defines the state of the link. Links with lower costs are preferred to links with higher cost. If the cost of the link is infinity, it means that the link does not exist or has been broken. To create a least cost tree with this method, each node needs to have a complete map of the network, which means it needs to know the state of each link. The collection of states for all links is called the Link State Database, or LSDB. There is only one LSDB for the whole internet. Each node needs to have a duplicate of it to be able to create the least cost tree. The LSDB can be represented as a two-dimensional array in which the value of each cell defines the cost of the corresponding link. Each node can create LSDB that contains information about the whole internet through a process called flooding. Each node can send some greeting messages to all its immediate neighbors to collect two pieces of information for each neighboring node: the identity of the node and the cost of the link. The combination of these two pieces of information is called the LS packet, or LSP. The LSP is sent out of each interface. When a node receives an LSP from one of its interfaces, it compares the LSP with a copy it may already have. If the newly arrived LSP is older than the one it has, it discards the LSP. If it is newer of the first one received, the node discards the old LSP and keeps the received one. It then sends a copy of it out of each interface, except the one from which the packet arrived. This guarantees that flooding stops somewhere in the network. To create a least cost tree for itself, using the shared LSDB, each node needs to run the famous Dijkstra algorithm. This iterative algorithm uses the following steps. First, the node chooses itself as the root of the tree, creating a tree with a single node, and sets the total cost of each node based on the information in the LSDB. Second, the node selects one node among all nodes not in the tree, which is closest to the root, and adds this to the tree. After this node is added to the tree, the cost of all other nodes not in the tree needs to be updated because the paths may have been changed. Third, the node repeats step 2 until all nodes are added to the tree. Both link state and distance vector routing are based on the least cost goal. However, there are instances where this goal is not the priority. For example, assume that there are some routers in the internet that the sender wants to prevent its packet from going through. Aside from safety and security, there are occasions in which the goal of routing is merely reachability, to allow the packet to reach its destination more efficiently without assigning cost to the route. To respond to these demands, a third routing algorithm called path vector routing has been devised. Path vector routing does not have the drawbacks of link state or distance vector routing because it is not based on least cost routing. The best route is determined by the source using the policy it imposes on the route. In other words, the source can control the path. Path vector routing is not actually used in an internet, but is mostly designed to route a packet between ISPs. In path vector routing, the path from a source to all destinations is also determined by the best spanning tree. The best spanning tree is not the least cost tree. It is the tree determined by the source when it imposes its own policy. If there is more than one route to a destination, the source can choose the route that meets its policy best. A source may apply several policies at the same time. One of the common policies uses the minimum number of nodes to be visited. Another common policy is to avoid some nodes as the middle node in a route. Path vector routing, like distance vector routing, is an asynchronous and distributed routing algorithm. The spanning trees are made gradually and asynchronously by each node. When a node is booted, it creates a path vector based on the information it can obtain about its immediate neighbor. A node sends greeting messages to its immediate neighbors to collect these pieces of information. Each node, after the creation of the initial path vector, sends it to all its immediate neighbors. Each node, when it receives a path vector from a neighbor, updates its path vector using an equation similar to the Bellman-Ford, but applying its own policy instead of looking for the least cost. The policy is defined by selecting the best of multiple paths. Here is a probable implementation of each routing protocol. Here, the packets needs to go from router 1 to router 5. There are several paths that can be used with different bandwidth capacity. For distance vector routing, it will go this way. For link state routing, it will go this way. For path vector routing, there is a policy that it cannot go from router 1 to router 4. So the path may go this way or this way. This ends Module 21. Thank you.